This is Lab 1 for Physics 2212, Charge Tapes by iishim Oberoi. To start off, the purpose of this lab is to create charged pieces of tape, observe their interactions with each other and objects in the environment, and calculate the exact charge on these tapes. By the end of this experiment, we should be able to observe real-life interactions and, given reasonable assumptions, use physics principles to calculate approximate but accurate answers. The physical principles in this lab are Newton's second law, F equals ma, or in our case, the sum of the forces equals 0, force due to gravity, Fg, and Coulomb's law, E net. The application of Coulomb's law will be in force electric on the point charge. The main results of this experiment were that the charged tapes repelled each other. The tapes were negatively charged with an approximate charge of negative 2.3 e to the negative 8 coulombs and had a surplus of approximately 1.4 e to the 11 electrons. We will be using a simplified model for this experiment in which each tape is represented by a point charge with the force F of g and F electric on them. The system would just be the singular tape, the floating one, and the surroundings is every other object including the second tape. The assumptions we've made is that both tapes have the same net charge, both tapes can be modeled as point charges, and the electrons are uniformly distributed along the tape. Moving on to our experiment now, our initial conditions were that we had a piece of tape that was considered neutral stuck to a flat surface. The tape coming out of the roll was assumed to be neutral, and the objects used to suspend the tape were also considered neutral. The first part of our experiment is to determine the sign of the charged tape. To do this, we took a piece of tape, tape A, smoothed it down onto the base tape and removed it very quickly to charge it, and then suspended it from a neutral object or at the edge of the desk. We then repeated the process, creating a second charged tape B, and brought tapes A and B close together and observed that they repelled. Then, bringing a neutral object such as my hand or a book close to tape A caused it to be attracted to the object. Finally, using a plastic pen and a cloth, we negatively charged the plastic pen and brought it close to tape A and observed that they repelled each other. From this, we can assume that tape A is negatively charged as it repels other negative objects and is attracted to neutral objects. The second part of our experiment would be to determine the actual charge of the tape. We repeat the previous process, creating two charged tapes, A and B. We then suspend tape B horizontally using two neutral objects with some slack of tape B in the middle. We place tape A below tape B and slowly bring it up until tape B begins to float. The distance between tape A and tape B is then measured. For our calculations, we can start off by determining the force due to gravity, which is the mass times the acceleration due to gravity. The mass is equal to the length density times the length, which is about 2.9 e to the negative 4 kilograms. Multiplying that by the acceleration due to gravity gives us 2.87 e to the negative 3 newtons. Now, using Newton's second law and separation distance d, which we measured to be 0.04 meters, we can have the formula force due to gravity is equal to force electric, which is constant k times qb, the charge of the tape, squared, divided by the distance d squared. This all gives us with a final charge of 2.259 e to the negative 8 coulombs, and this is the absolute value. The charge would actually be negative since the force vector is pointed downwards. And for the number of electrons, we can determine that by simply dividing the previous charge by the charge of one electron, which gives us 1.4 e to the 11 electrons. As an additional calculation, we can determine the ratio of atoms to electrons by taking the area of the tape and dividing it by the area of an atom, and then finally taking the number of atoms and dividing that by the number of electrons. In my code, the red sphere is tape B, the floating tape, and the blue sphere is tape A. The cyan-colored arrow is the force electric vertically upwards on the red sphere, and the orange arrow is the force of gravity downwards. In my code, you can see the section for constants, particles, calculations, and the rest is just visualization. The difference between our model and reality is that the tapes are not true point charges, the tapes were not the exact same length, and the model does not account for outside attractive forces, such as the two neutral objects used to suspend the floating tape would have exerted an attractive charge on said floating tape. Now, the possible sources of error are that the tapes would have lost charges as they were being handled. The distance between the tapes could have been skewed because as the ruler was brought closer to the tapes, the neutral matter would have attracted the two, shortening the distance between the two tapes. And finally, unequal charge distribution on each tape is possible. If electrons and protons switch charges, the interactions between two charged tapes and between a charged tape and a neutral matter would remain the same. However, interaction between a charged tape and a negatively charged object would be the opposite, wherein the charged tape would be attracted to it. It's important to handle the tape as little as possible because the more you touch it, your fingers receive electrons from the tape and thereby weakens the charge on the tape. From this experiment, we can conclude that by simply rubbing or touching, objects can become charged. And by making general assumptions, we can use physics principles to determine quantitative data and explain real-life phenomena.